This lecture is about spherical mirrors. Now, paradoxically, we're going to start by talking about flat mirrors because they're easier to think about. So I've drawn here a flat mirror, and this dotted line represents a normal vector to that surface. In other words, this is just a line that's at a right angle to the surface of the flat mirror. Now here is an incident light ray approaching the mirror, and here's the outgoing reflected light ray. The angle that these two rays make relative to the normal to the surface of the mirror is equal. So they're both theta. If one is theta, the other is theta. It would be equivalent to say that these two angles are also equal. This is sometimes called the law of reflection. Now we'll talk for a moment about image formation in mirrors. Here's a flat mirror, and here's an object. Now our eyes detect objects by detecting the light rays that are bouncing off of them, that are coming from those objects. And where those light rays intersect is the location of the object, and that's actually how our depth perception works, and how we perceive distance to objects. At least part of how we perceive distance to objects is where the light rays intersect. Now when there's a mirror present, there's another pair of light rays that we will perceive coming from the object, a pair of reflected light rays. And where those light rays appear to intersect, or would intersect if they continued back behind the mirror, we then perceive an image, a reflection. Now note that these two reflected light rays, they don't actually intersect. The light rays incoming to the mirror do intersect, but the reflected light rays don't actually intersect. If they are extrapolated backwards behind the mirror, they do intersect. And where the extrapolation intersects, we still perceive an image. Because the light rays don't actually intersect, only the backward extrapolation of them intersects, this gets a special name. This is called a virtual image. If the reflected rays actually intersect, that's called a real image. Now we don't get a real image with a flat mirror, but we will get a real image with spherical mirrors, which we turn to now. Now spherical mirrors actually are an approximation to parabolic mirrors, and parabolic mirrors have a very special property, which is that incoming parallel light rays reflected off of a parabolic mirror will all pass through a point called the focus of the mirror. Now this property is pretty hard to show for parabolic mirrors, but it's easier to show for spherical mirrors, which also have this property approximately. So we'll focus on the case of spherical mirrors. The nice thing about a spherical mirror is that it has a center, which I've drawn here, and from that center out to the edge of the spherical mirror, well, out to the sphere, the spherical mirror itself, we can draw a radius. And this radius is geometrically always at a right angle to the mirror itself. That means that this is a normal to the surface. And the law of reflection then states that these two angles are equal. We'll call them both theta. Now we need to do some geometry. Here are two right triangles we can draw. This angle is also theta because these two lines are parallel and this line intersects them both, so this angle and this angle are equal. This angle is 2 theta because, again, these two lines are parallel, this line intersects them both. The total angle here is 2 theta, so this is also 2 theta. We'll call this distance the focal length. It's the distance at which the reflected ray intersects this axis, the distance from the mirror. This we'll just call h, it's going to wind up disappearing. And this distance is the radius of the mirror itself, the distance from the center of the mirror out to the mirror itself. It's the radius of that spherical mirror. Now looking at the blue triangle, the tangent of theta is h over r, and the tangent of 2 theta is h over f from looking at the orange triangle. Now the approximating assumption that we make is that theta is small. And theta is going to be small as long as we're pretty close to the center of the mirror. And this is the way in which spherical mirrors only approximately have the behavior of a parabolic mirror. They approximate a spherical mirror, but you have to be pretty close to the center of the mirror so that theta is not too big. Now in that case we can use the small angles approximation, which says, among other things, that the tangent of theta is approximately just theta for theta much less than 1 radian, that is. So working in this approximation, theta is equal to h over r. That's because tan theta was just theta, so theta is h over r. And 2 theta is h over f. And a little algebra will get you to f equals r over 2. So the focal length is the radius over 2. Now, note that h totally disappeared. And this is important because it means regardless of h, any incoming parallel ray will come to the same focus. So a parallel ray here will come to that focus at radius over 2. Parallel ray here will come to that focus at radius over 2. And so on. This decluttered drawing might help with visualization. The point is that incoming parallel rays will all converge at the same focus. Okay, let's look at some implications of this in terms of image formation. Here's an object, and we're going to see where the rays that come from this object and bounce off the mirror intersect. In order to do that, we can trace a couple of rays. So I'll start with a parallel ray. When reflected, it passes through the focus. Now, these rays, mirrors work the same forwards as backwards, so there's another ray we can draw which passes through the focus, and when it's reflected, it's parallel. Through the focus, reflected rays parallel. So the image forms where the rays intersect, so that's where the image forms. Now this is an example of a real image because the reflected rays are both actually intersecting here. Unlike in the case of the flat mirror where the reflected rays didn't actually intersect, we had to extrapolate them back behind the mirror, and that's called an imaginary, virtual image. This is a real image. Note that the image is a little bit smaller than the original object, and the image is also flipped upside down. Let's consider a couple more cases. Let's consider the case of an object somewhat closer to the focal point. Incoming parallel ray, reflected ray goes through the focus. Incoming ray through the focus, reflected ray becomes parallel. There's the image. It's another real image, but note that the situation is somewhat reversed from before, because before we had a larger object and a smaller image. Now we have a smaller object and a larger image. So this case was the image is magnified rather than shrunken. It is again upside down. Let's consider a third case of the object actually inside the focal length. Parallel incident ray, reflected ray passes through the focus. Now the incident ray that passes through the focus isn't so simple. Of course, if a ray comes from the object and passes through the focus, it never hits the mirror. So what we have to consider is a ray whose backwards extrapolation passes through the focus but is actually moving away from the focus towards the mirror. So here it is. And the reflected ray is parallel. Now I'm highlighting the reflected rays in orange here because for the purpose of understanding the image formation, we need to look at the reflected rays and find where they intersect. Now as we can see, they won't intersect in front of the mirror. It's their backwards extrapolations that will intersect behind the mirror. So there's the image. And this is a virtual image because the reflected rays are not actually intersecting. It's just their backwards extrapolation. Put another way, the image is behind the mirror. So that's a virtual image. Note that it's not flipped upside down this time, and also note it's magnified, it's bigger. Now the mirrors we've been discussing so far are all concave mirrors. What about convex mirrors? These will have a focal point behind the mirror, and in this case, the incoming parallel rays will be reflected such that their reflected rays, the backward extrapolation of the reflected rays, passes through the focus. Now, I'm not going to prove this, but the geometric proof is very similar to the geometric proof for the concave mirror. Actually, that's a great idea. Homework problem 1. Prove this, that with a convex mirror, the reflected rays, the backwards extrapolation of the reflected rays, all pass through the focus, that is, for incoming parallel rays. The focal length will again be radius over 2, and it's a geometric proof similar to the one I already showed you for the concave mirror. So now let's look at image formation with the convex spherical mirror. Incoming parallel ray, outgoing ray passes through the focus, that is, this backwards extrapolation does. An incoming ray whose forwards extrapolation passes through the focus. The reflected ray is parallel. I'm highlighting the two reflected rays in orange to help us find their backwards extrapolations. There's one. The other one is parallel. The image forms there. It's smaller, so it's shrunken, and but it's right side up, and it's a virtual image. So it's good to note how much we were able to do without really having to use any equations to describe these situations. Just by doing geometry, drawing some lines, seeing where they intersect, we're able to learn a lot about spherical mirrors and when they magnify and when they shrink and what turns upside down versus right side up. Let's do a sample problem and then a homework problem with geometric optics now. Now some people have on a door a handy mirror that hangs over the top of the door, so that you can see in the mirror how you look in the morning. Now we'd like this mirror to be wide enough and tall enough so that you can see your entire self in the mirror. Let's consider a person who's 6 feet tall and 3 feet wide. And for the sample problem, the question is, how wide does the mirror have to be in order for a 3-foot wide person to be able to see their full self? Let's draw a top-down view. So here's a top-down view of the person. There's their head and their 2 shoulders, and they're 3 feet wide. And here's the mirror in front of them. Now they want a light ray to be able to bounce off their right shoulder, reflect off the mirror, and come to their eye, which is roughly in the center of their body, a little bit off center. And same on the left shoulder. Well, these are all congruent triangles, these 3 triangles right here. And so, if 3 feet is equal to 2 times the side length of the shorter side, then the mirror has got to be at least 1 times the side length of the shorter side. The side length of the shorter side is 3 feet over 2, so the mirror's got to be at least 3 feet over 2 wide, 1.5 feet wide. So that tells us how wide the mirror has to be. Now for homework, how close to the ground does the mirror have to be? How close to the floor does the mirror have to be in order for this person to be able to see their feet? That's homework problem 2. How close to the floor does it have to be? In other words, what is the maximal value of h that will allow this person to be able to see their feet? We're now going to derive something called the lens equation. Let's consider this situation, and let's label this angle theta and this angle phi, not necessarily the same angle. Let's call this height h. Now by geometry, this angle is theta and this angle is phi. And note that this length here is the focal length. And from these 2 right triangles that are formed, we have that f tangent of theta, which is this height, plus f tangent of phi, which is this height, is equal to h. Dividing both sides by f, we get this. Note from geometry that this angle is phi, and this angle is theta. If we call this distance the object distance, careful not to confuse that O with a 0, it's the object distance, the distance between the object and the mirror. And we call this distance the image distance, the distance between the image and the mirror. Then from this triangle, we get that the tangent of phi is h over O, and from the other triangle, we get that the tangent of phi is h over I. Substituting into this equation, we get h over O plus h over I equals h over f. Canceling out the h's, we are finally left with the lens equation. 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Now, one important thing to note about the lens equation is that even though we derived it here in the context of a concave mirror, it works for a convex mirror as well, as long as with a convex mirror we understand the focal length to be a negative number. And in fact, that convention we can extend a little bit further. For mirrors, anything to the right of the mirror is a negative number. So this would be a negative focal length, a negative image distance, and with those sign conventions, the lens equation works just fine. Similarly, this would be a negative image distance. Anything to the right of the mirror is a negative number. These are both positive image distances. So with these sign conventions, the lens equation works for both concave and convex mirrors. Now you'll note I'm calling it the lens equation. It actually works for lenses as well as mirrors, and we'll get to those in the next video. Now we've been talking a little bit about magnification. We can define it mathematically as minus the image distance over the object distance. And so in that case, whenever we have a positive object distance and a positive image distance, we get a negative magnification. Negative magnification means that the object is flipped upside down. And we see that pattern manifested. Here, where we had a negative image distance, because of this minus sign, the magnification becomes positive. And as we see that, again, now the positive magnification corresponds to a right side up image. So negative magnification means a flipped image, and when the magnification is positive, that means the image is right side up. Magnification larger than 1 means it's enlarged. Between 0 and 1 means the image is shrunken. Let's do a sample problem. Suppose we have a concave mirror with a focal length of 8 centimeters and an object distance of 12 centimeters. If you're wondering how this person can possibly be so tiny, being only 12 centimeters away from the mirror, that's a good question. I guess this is just a little action figure or something. So the question is, what is the magnification? Now just by drawing, we can get some idea of what the magnification should be. And this is helpful, so we see from the drawing that the image will be inverted. That means the magnification should be negative. And the image is enlarged. That means the magnification should be negative and more negative than negative 1. So it should be less than negative 1. So let's now use the equation and see what it actually turns out to be. Here's the lens equation. Solving for the image distance, we get this. Putting in numbers, that gives an image distance of 24 centimeters. And that gives us a magnification of minus 2. As we expected, the answer is less than negative 1. For the third homework problem, consider an object positioned 16 centimeters away from the mirror and determine the magnification.